All right, so in general, if our function is continuous, then the endpoint, both left and right endpoint, together with the midpoint approximations, as you increase the number of rectangles, all of these schemes will provide the same result. So, in general, a limit as the number of rectangles n goes to infinity, this will give us the true area under the curve. So using this, let's go ahead and find the true area under the graph of this parabola over 0 to 1. So same function as the previous example, but because we are using an indeterminate, or not indeterminate, but a arbitrary number of rectangles, we're letting n stay arbitrary. We're not fixing it to a specific real number, or integer value at least. So we're going to just leave n as capital N. So here, what does that change? Well, a and b, they stay the same. So a is 0, b is 1, n is just n. So I'm not even going to write n equals n. I'm just going to say n rectangles. So these three things imply that delta x is 1 minus 0 over n, so 1/n. Now, it doesn't say to use the right, the left, or the midpoint, but this theorem does say that no matter which one you use, as long as your function is continuous, then they will all approach the same value. So it doesn't matter which one we pick. I usually find the right endpoint approximation to be easiest, but that's not necessarily true. Depends on the function. But because we did the right endpoint approximation up here, we should probably just still use it since we sort of already kind of know where it's going to go. So in this case, we'll say that x sub I is 0 plus I times delta x, a plus I times delta x, which is 0 plus I over n, which is just I over n. Therefore, f of x sub I is I squared over n squared minus I over n plus 1. So now, our r sub n is the sum from I equals 1 to n of this whole expression times delta x, which is 1/n. Okay? So, what I'll do here is very similar to what we did in the previous section. I'll factor out these 1 over n, n squared, n cubed. So we'll have a 1 over n cubed sum from I equals 1 to n of I squared minus 1 over n squared sum from I equals 1 to n of I plus 1 over n sum from I equals 1 to n of just 1. So using our power sum formulas, this one should turn into n times n plus 1 times 2n plus 1 all over 6 minus 1 over n squared. Power sum formula here is n times n plus 1 over 2 plus 1 over n. Power sum formula here is just n. So simplifying this, actually, we'll do this up here. So r sub n does look something like, if we cancel out what we can, we should have n plus 1 times 2n plus 1 all over 6n squared, I believe. Yep, because this n cancel with one of these n's down here, so we should just have n squared left over in the bottom. Here, again, we'll cancel that n, so we'll have one n left in the bottom, so we'll have a 2n in the bottom. So this will be n plus 1 over 2n. And this will be plus 1. So now if we take the limit as n goes to infinity of r sub n, I'm going to take a limit of each of these three terms. Well, this term here, we're going to use dominating terms. So what kind of degree polynomial do we have in the numerator? If, not that we have to, but if we were to FOIL this out in the numerator, the leading term would come from the leading term of this term times the leading term of this term, which would be n times 2n, which is 2n squared. So the biggest degree term in the numerator is 2n squared, and 6n squared in the bottom. Remember that if the degree of the top equals the degree of the bottom, which we do, quadratic over quadratic, then the limit of this expression as n goes to infinity is just the ratio of the leading terms. So 2n squared over 6n squared, this is just 2/6, which is 1/3. So this is 1/3. Minus, same thing. This is the first degree polynomial on the top, first degree polynomial on the bottom. So the limit of this expression as n goes to infinity is n over 2n, which is 1/2. So this is minus 1/2. Plus, there's no n's in this term, so the limit of it as n goes to infinity is just itself. So 1/3 minus 1/2 plus 1. So this is 1/3 plus 1/2. Common denominator is 6, so this would be 2 plus 3 over 6, which is 5/6. And that is the true area under the curve.